They're seeing speedups anywhere from 10 to 40 times. About 100 functions have already been programmed to CUDA, and more will happen. Our engineers and theirs are working closely together to continue to fine-tune and enhance the capability of MATLAB. Now GPU computing is instantaneously available to 1 million users around the world who are doing important work, who are doing work in the area of high productivity research or analysis or development. I don't know a single technical company in the world, and certainly we use it, doesn't use MATLAB around in their work in some way. Really, really important. This is the Excel of engineering. A big announcement today, and I'm very excited about that. Let's congratulate the folks at MATLAB, please. Computational biology is one of the areas that is just really, really exciting. There's all kinds of ways that people are using high-performance computing in pharmas and research in universities to advance their knowledge of living things and to help discover the next wonderful drug that can cure cancer, for example. There's a whole lot of different areas where high-performance computing can benefit the research. It could be in the area of molecular dynamic simulation, where atoms and molecules are simulated using approximated Newtonian physics so that researchers can understand how a molecule, when attached to another molecule, would conform, how its shape would change based on the nature of that protein or molecule. In order to do this simulation, it takes an enormous amount of computational resources, and you have to simulate it in long enough so that you can gain some insight. These are biological things. And so you need to simulate it long enough. Suppose you wanted to simulate, you want to understand how somebody walks. You have to simulate long enough to take the full step. So you can't just simulate for a short period of time. You need to reduce the size of your models to the point where you can simulate it to achieve some kind of understanding. 5,000 nanoseconds is a very typical simulation to understand how molecules would bind and conform as they come close to each other or attached to each other. That's one example. Another example is just to compare the gene sequence of various proteins. Various proteins with similar gene sequences have similar chemical behavior. And so once they understand the chemical behavior of a large number of proteins, they can compare a new protein or a new discovery against that, a new molecule against that large database. So comparing gene sequences, a very important application, enormously computationally intensive. Researchers are now simulating molecules at the electronic level, at the atomic level, using quantum physics principles. And they call that, using quantum mechanics principles, and they call that quantum chemistry. Games is an example of that, Gaussian is an example of that. So there's a large body of work that's related to advancing research in computational biology, and it all requires an enormous amount of computational resources. Being able to parallelize the application is a very big deal. Now, AMBER is one of the leading nanomolecular dynamic simulators. Along with CHARM, NAMD, GROMACS, they represent the vast majority of the most popular molecular simulation packages in the world. The team at UCSD, San Diego Supercomputing Center, led by Ross Walker, recently took the AMBER 11 simulator and made it multi-GPU ready, multi-GPU capable. And the work and the results are fabulous. The speed up is really, really impressive. This is the JAC benchmark. The JAC benchmark, I think, stands for Joint AMBER CHARM Benchmark. This represents about 24,000 atoms. And these 24,000 atoms is basically a protein immersed in water. And they simulate this particular simulation for using it to compare various computing configurations. With Ross Walker and his team's work, we're now able to run on 8 Fermi GPUs, and this is run on the IBM iDataplex cluster with 8 GPUs inside, we can achieve 52 nanoseconds per day. In 1 day's time, these 8 GPUs can simulate 52 nanoseconds. Just think about this for a second. Suppose you wanted to simulate for 5,000 nanoseconds. This 8 GPU cluster will still take 10 days. However, on the fastest supercomputer that's been run, this is run on the Kraken supercomputer at Oak Ridge. Those 8 Fermi GPU cores, completing 52 nanoseconds per day, is up against Kraken, which completes 46 nanoseconds per day. Now, when you look at these graphs, you can tell that the GPU speedup is surely dramatic. But graphs don't tell the whole picture. It's when you look at it in the context of the physical world that you realize the benefits of GPU computing. The Kraken is a massive supercomputer. It is a multi-tens of millions of dollar installation. It is the fastest Amber machine in the world today. And with an 8 GPU cluster running Amber 11 with MPI for GPUs that Ross Walker and his team did,